Welcome to Chapter 4 of our CompTIA Network Plus Guide to Networks. Today we're going to explore protocols, which are the fundamental rules and standards that govern how network devices communicate with each other. Think of protocols as the main traffic logs of networking. They ensure data flows efficiently and safely across networks. And without these standardized communication rules, devices from different manufacturers wouldn't be able to understand each other, and our interconnected digital world simply wouldn't function. So let's dive into the essential protocols that make modern networking possible. In this video, we've got 4 big goals, and by the end, you'll know how the main protocols like TCP/IP work. They're basically the internet's dynamic duo. How to secure your data with encryption. It's like putting your secrets in a digital vault. How to set up remote connections. And this is how you can work from your couch or your coffee shop. And finally, we'll talk about tools you can use to fix things when the network decides to have a bad day. Because let's face it, it happens. First, we're going to look at TCP/IP core protocols. And when we talk about that, I want you to imagine you're sending a letter. Before it can go in the mailbox, it needs a few things. First, you need to write the message, and that message is what's called your payload. Then you put that into an envelope, and that envelope is like a header added at the transport layer. Next, you put that envelope in a box with the address on it, and that's the network layer adding its own header and turning it into a packet. And then finally, the mail carrier puts it in their bag with a bunch of other letters, which is like the data link layer, creating a frame with a header and a trailer. When it's all ready, it's sent on its way down the road to the physical layer. So if you look at the diagram, here's our journey of our data that's visualized. Notice how each layer talks to its corresponding layer on the other side. It's like a game of telephone, but instead of the message getting garbled, it actually arrives intact. The browser on the left is basically saying, "Hey, web server, send me that cat video." And the web server responds, "Coming right up," all while following proper protocol etiquette. Devices like routers and switches and firewalls all read different layers of your data, as shown with the diagram on the left there. Think of it like a party. Some people only check your ID at the door. That would represent the data link layer. Others actually read the address to make sure you're in the right house. And that's the network layer there in green. Some people want to know your whole life story. And that's the transport layer, which is in blue. The higher the device reads in the OSI model, the more detail it gets about your packet. Basically, some are strict bouncers and some are nosy neighbors. TCP lives at the transport layer, and it's the overly cautious friend of networking, so to speak. It refuses to send a single word until it knows that you're ready to listen. TCP is connection oriented, meaning it starts with a handshake like a polite business meeting. It also checks every little detail, sequencing, checksums, and flow control. If one piece is missing, it says, "Nope, not moving forward until this is fixed." Sure, it can be a little slow, but it's reliable, kind of like sending puzzle pieces in the mail. TCP makes sure they all arrive in the right order and none of them are bent. So here's what a TCP segment looks like. It's busier, really, than a smartphone screen. You've got source and destination ports, like apartment numbers, sequence numbers, because order does matter, acknowledgement numbers, basically saying, "Got it," and various flags that are like emojis for networks. The checksum is there to catch errors because nobody likes corrupted data. It's the equivalent of digital food poisoning. Now, before TCP actually transmits your data, it performs a 3-way handshake. Think of it as the world's most formal texting conversation. For instance, I say, hey, are you online? That's the SYN, the SYN. Friend says, yeah, I'm here. You ready? That's the acknowledgement, the ACK. Then I say, cool, let's start. That's another acknowledgement. After this digital nice to meet you ritual, does the real conversation does happen. So I have to request the connection. It has to respond to me, and then I have to respond back. Every time you send data, that has to happen again. All three pieces. TCP keeps track of the sequence numbers like a parent counting kids in the minivan, like Home Alone, except Home Alone, they really screwed up. Here's the three-way handshake in action. So this is kind of what it looks like in a diagram form. Computer A in this visual starts with a sequence number, and that sequence number is 937013558. That's like giving out your phone number, but it's kind of random. Computer B responds with its own number and acknowledges A's, and you can see that number. Finally, A says, I got your message, and the connection is established. It's like a secret handshake, but there's more math involved, and it's not as cool. So let's meet TCP's reckless cousin, and that would be UDP. Unlike TCP, UDP doesn't bother with handshakes. It doesn't check anything or do anything with flow control. It just throws data in the network like, here, take it. Whether you catch it or not, that's your problem. Sounds bad? It is. But on the other side, for streaming video, online games, live sports, it's perfect. Imagine watching a soccer game. You'd rather miss one frame than wait 3 minutes for the perfect replay to buffer. UDP is faster and lighter because it skips all the polite conversations. It's like the you only live once of internet protocols. Shifting gears a little bit, this slide talks about IP, which is the Internet Protocol. IP is the GPS of the networking world, and its job is to figure out where data is supposed to go and where it came from. Each data packet gets a to and from address, just like writing an envelope. But here's the kicker. IP is actually connectionless. That means it doesn't ask, hey, are you ready for me to send this? Nope, just drops the packet on the road and says, good luck. It's like the pizza delivery driver who throws the pizza on your porch without even knocking. It's not really perfect or ideal, but it does get the job done. So this is an example of an IPv4 packet. It's got more fields than a farmer's almanac, if you know what a farmer's almanac is. You've got version numbers, which are like software updates. You've got header links, and size does matter with header length. And then you've got that very important TTL field, which is time to live. TTL is like a packet's expiration date. It prevents packets from wandering the internet forever like digital zombies. The data section there at the bottom carries either a TCP segment or a UDP datagram. And that area is kind of like the VIP section for information that's actually useful. And we also have IPv6, which is the newer, shinier version of IP. And why did we need IPv6? Because we ran out of IPv4 addresses. It's like running out of phone numbers in your area code. IPv6 uses much longer addresses, which means there are enough for every person, every device, and probably every toaster on Earth. IPv6 also moves packets more efficient by removing some unnecessary baggage. It's kind of like upgrading from a tiny dorm fridge to a full-size refrigerator where you finally have room for everything. Next, we have the ICMP, which is the tattletale of your network, to be honest with you. Its job is to report back when something goes wrong. Did a packet get lost? Is a router too busy? Did a packet expire? ICMP will let you know if that happens. But don't expect it to fix the problem. It's just there to point fingers. It's like the coworker who says, hey, the printer's jammed, but doesn't actually fix it. Still, Tools like ping and traceroute rely on ICMP, so it's actually a pretty useful tattletale. Now we move on to address resolution protocol on IPv4 networks, which is shortened to another acronym called ARP. And ARP is like the phone book of networking. It works with IPv4 to find MAC addresses on the local network. Kind of like when you know someone's name, that would be the IP address, but you don't know their phone number. The phone number would be their MAC address. ARP broadcasts a message saying, hey, who has this phone number? And the device responds, that's me. Here's my MAC address. It's layer 2 protocol that relies on broadcasting, basically shouting across the digital neighborhood. Your computer does keep an ARP table, which is basically a cheat sheet that remembers which IP addresses go with which MAC address. There are two kinds of entries. There are dynamic, which are created automatically when needed, and static, which are manually entered. You can even view this yourself, as shown at the bottom of this slide, by using the ARP space -A command in Windows. It's kind of like snooping on your computer's contact list. Here's what it looks like when you run that command on your computer. You'll see a list of all the devices your computer has recently talked to, along with their MAC address. It's like looking at your recent phone calls on your phone, except instead of people, it's printers, routers, and random information technology gadgets that you really probably forgot you owned. In IPv6, ARP gets replaced by something smarter, and it's called Network Discovery Protocol, or NDP, another acronym. It does the same thing, but it does have some extra features. NDP automatically figures out who's nearby, detects when a device disappears, and even asks routers for directions. It's like ARP, but with GPS, social networking, and a sixth sense. It's basically the more modern, well rounded cousin that makes IPv4 ARP look a little outdated. Moving on to Ethernet. Ethernet, honestly, is the real MVP of the data link standards. It's like the universal translator for networking. It runs on various media types. It offers excellent performance at a reasonable cost, and it's honestly more popular than cat videos on modern networks. Ethernet 2 is the current standard because Ethernet 1 was like the beta version, and it adds both a header and a trailer to create a frame, which is like putting your data in a protective envelope with return address labels. An Ethernet frame is like a sandwich. You've got your payload in the middle, and that's the actual data. Then you've got the header and the trailer, like the bread holding everything together. The header has source and destination info, while the trailer has error checking. The whole thing is usually 46 to 1500 bytes of data. But in some special cases, you can make a jumbo frame of about 9,000 bytes. That's like ordering a foot-long sandwich when everyone else has just a 6-inch sub. Diagram of what Ethernet 2 frame looks like. Think of it like a wrapped package with a gift tag. The tag says who it's from, who it's for. The box itself is the payload, and the tape at the bottom, which is the trailer, checks that nothing got ripped up along the way. Without this, your package could show up at grandma's house looking like a raccoon torn apart. Encryption protocols are they actually use mathematical codes called ciphers to scramble data, like creating secret languages that only authorized people can understand. Encryption is evaluated on 3 criteria that form the CIA triad, which is confidentiality, which it keeps secrets secret, integrity, and that integrity makes sure data isn't tampered with, and availability, which ensures that data is accessible when needed. Think of it like a three-legged stool of security. If you take one of those legs off, everything falls over. With encryption, it uses keys. Think of it as a super complicated password that scrambles your message into unreadable code called ciphertext. With symmetric encryption, one key is used for both locking and unlocking, kind of like a secret shared handshake. With asymmetric encryption, there are two keys: a private one you keep hidden and a public one that you can hand out to anyone. It's like having a mailbox. People can drop letters in with the public key, but the only person that can open it is the person with the private key. Keys do come with certificates, kind of like digital ID cards. These are issued by certificate authors, or CAs, another acronym. They are trusted third parties that say, yep, this person is who they claim to be. This whole system is called, guess what? Another acronym, PKI, which stands for Public Key Infrastructure. It's like the DMV for the internet. It issues IDs, it checks authenticity, and it lets you prove who you are, who you say you are. Without certificates, anyone could pretend to be your bank, and you'd end up wiring money to some guy that you would have no idea who he is. The kicker is that keys are not forever. They have a life cycle. They're born, they get stored, they get rotated, and then they eventually get retired. Managing all of this is called key management, and it is super important. If someone forgets to rotate an old key, hackers can sneak in, like someone using an expired employee badge that still works. Proper key management keeps your digital vaults locked tight and your secrets safe. Moving on to SSL and TLS, they are, well, you can see what they stand for: Secure Sockets Layer and Transport Layer Security. Once again, more acronyms. They really are kind of the superheroes of security for the internet, because they encrypt data between computers and websites. That little padlock that you see at the top left part of your browser by the URL, that's TLS at work. Before your computer and the server can talk, they perform a handshake, kind of like agreeing on the rules of the game. Okay, we'll use this encryption. Ready? Sure. Only once they agree does the real conversation start. Without TLS, logging into your bank account would be like shouting your password across a crowded room. Next, we have Internet Protocol Security, which is abbreviated to IPsec. The IPsec is like a Swiss Army knife for secure networking. It's a whole suite of tools that encrypts, authenticates, and manages keys for those TCP/IP transmissions. It sets up secure connections in 5 steps. We've got the initiation, key management, negotiations, data transfer, and termination. Basically, it's like setting up a secure Zoom call: shake hands, agree on the rules, talk privately, then hang up. Remote access protocols is what lets you log into a computer that's across town or even maybe across the world. It's the magic behind IT support taking over your screen to fix your computer. There are a few different flavors of remote access. We've got remote file access, where you share documents. You've got terminal emulation, which is when you control another machine like you're sitting at it. You've got VPNs, which is creating a secure tunnel to another network. Without remote access, we'd all have to fix our relatives' computers by actually driving to their house. Next, we have File Transfer Protocol, FTP. That is like the OG of moving files around. But it's like mailing postcards as well. Anyone can read them along the way. It's not very secure. So as a result, we have FTPS, which is secure FTP, and that does add encryption. And then we have SFTP, which uses SSH for extra protection. And then there's TFTP, which stands for trivial FTP, which doesn't bother with security at all. That's like leaving an Amazon package on your porch and hope that nobody takes it. And you really need to use caution if using trivial FTP. Terminal emulation, which we briefly mentioned last slide, lets you use your computer to control another one, kind of like a remote control for TVs. You use command line tools like Telnet and SSH to type directly into another system. You can also use graphical tools like Remote Desktop, TeamViewer, or VNC if you prefer clicking over typing. It's really the closest thing to teleporting into another computer that we have. We also have Telnet that we just mentioned, digging a little bit deeper into it. It really was one of the first ways to remotely control computers, but it's not very secure. It's really about as secure as writing your password on a sticky note and putting it on your monitor. So as a result, SSH entered the scene, which stands for Secure Shell. That encrypts everything and it blocks common attacks like spoofing and eavesdropping. SSH is like Telnet's older sibling who learns street smarts and always locks the door. Next, we have, this is still part of terminal emulation, we have Remote Desktop Protocol, which is shortened by RDP. That's a Microsoft tool, and that lets you take over a computer with full graphical access. That's like being there in person, honestly. Then there's OOBM, which is out of band management. That is hardcore IT stuff where admins connect directly to network devices with a special management card. Even if it's the main network, even if the main network's down, they can still get in. And that's really kind of like having a secret backdoor into the server room. Then we have a VPN, which is a virtual private network. That's like digging a secret tunnel through the internet. It connects two networks or your computer to a network in a secure, encrypted way. You'll hear terms like site-to-site VPN, client-to-site VPN, or host-to-host VPN. No matter the type, the goal is the same, and that's to keep your traffic private. It's kind of like wrapping your data in an invisibility cloak so your nosy neighbors or hackers can't see what you're up to. VPNs do use tunneling to protect data, as we mentioned last slide. So think of it like putting your letter inside another envelope and then sending it through the mail. Even if someone opens the outer envelope, the real message is still sealed inside. That's what tunneling is. Some VPNs operate at the data link layer, some at the network layer, but they all rely on extra encryption to keep your tunnel safe. Without it, your secret tunnel would be more like a glass tube where everyone could see inside. Some common VPN tunneling protocols include L2TP, which is layer 2 tunneling protocol, GRE, which is generic routing encapsulation, OpenVPN, which is kind of the open source favorite, and then IKEv2, which stands for Internet Key Exchange version 2, obviously because version 1 wasn't good enough. Each one of these has its strengths, kind of like picking your favorite pizza topping. Some are fast, some are secure, some are flexible. The important part is that they keep your data safe as it travels through that secret tunnel. So moving into troubleshooting, and I think troubleshooting is kind of what we finish out with. Some examples. NetStat is an example, and that's like a network detective tool. It displays TCP/IP statistics and connection details, telling you which ports are running services, like seeing which doors are open in your digital house, which connections are currently active, like who's visiting the house, how many messages interfaces have handled, which is kind of like the results of a popularity contest, and how many errors occurred. It's basically a comprehensive health report for your network. Another tool is Traceroute or TraceRT in Windows. And what that does is it maps the path your data takes to reach its destination. Each router along the way gets pinged and you see the journey step by step. It's like using GPS to trace your road trip. First we went through Chicago, then Indianapolis, then Louisville, so on. And if a packet gets lost, traceroute shows you where it got stuck, which is why it's a beneficial tool. Here's a diagram of what traceroute looks like in action. Each hop there is a router your packet is passed through, and the times show how long each leg of the journey took. If one hop looks way slower than the rest, bingo, you've just found your traffic jam. Another one is TCP dump, and that's a packet sniffer for Linux and Unix systems. It captures all the traffic going through your computer's network card so you can analyze it later. This is like putting a stethoscope on your network and listening for the heartbeat. It's pretty powerful stuff, but it's also pretty dangerous if it's misused. And that's why it usually requires admin permissions, because it's kind of like the network equivalent of wiretapping. So, solving some common problems. First problem is duplicate MAC addresses. And that's a fun one because every device should have its own unique MAC address. But sometimes mistakes or maybe even a malicious attack it happens and causes duplicates. And this is like two people showing up at a costume party wearing the exact same one-of-a-kind costume. It's confusing and it's a little awkward. On networks, it causes errors and it drops connections. And the fix is to track down the imposter and to update the configuration. And when hardware fails, like a router or switch dying, it's time to break out troubleshooting tools. Ping checks connectivity, traceroute follows the path, error messages help you find the broken link. It's kind of like your doctor checking your pulse, your blood pressure, running an x-ray to find the problem. Once you identify the failing device, it's usually as simple as replacing it, although we all know nothing is simple or, that simple whenever you're dealing with networking. So, chapter 4, that's a wrap. You learn that protocols are the rules of the digital road. You learn that TCP is reliable but slow. UDP is fast but reckless. And IP is the addressing system that keeps data moving. We covered encryption. We covered VPNs, troubleshooting, and even how to catch sneaky problems like duplicate MAC addresses. Basically, you've just leveled up from network newbie to network detective. That's it for chapter 4. I will see you in chapter 5.